Hello, my good students, friends, teachers, and all fans of Dr. Sirme YouTube channel. Thank you so much and Happy New Year 2023. For today, I want we go through KCSE 2022 Chemistry Paper 2. A paper that was done on 6th of December, the year 2022. Now, what I'm doing is to take you through the paper as it was presented to the student, as it was marked. And I know for the student preparing for KCSE 2023, it will be very useful for you. Thank you so much. This is Dr. Sirme. To start with, the question paper. Good. That is the cover page. As I've always said, the instructions are very important. My student, very important. Go through the instructions and, of course, attach your details accordingly. The grid for this one, the paper this time round had 7 questions. And you can see the distribution of marks per question there. The question total, the paper total, 80. Remember, this is a theory paper. Now, I want to take you through the areas that were examined. Yes. Let's start with question 1. Question 1 had an area on structure and bonding, and then a bigger portion of it, periodic table. You can see that is form 2 work, and the marks distribution there you can see. Question 2, it was a chemistry of alkanos, that is organic chemistry 2. That is the main part of question 2. Then there were some 3 marks there from energy change. Now you can see that is form 4 work. Question 3, electrochemistry. Yes, electrochemistry. And basically it was talking about electrochemical cell, then electrolysis, which is part of the electrochemistry, and that is form 4 work by student. Then question 4, rates of reaction or reaction rates, and maybe some 3 marks there from the equation or the chemical equation and mole concept. But the bigger portion of the question 4 was rates of reaction. Form 4 work and some bits of form 3. Then question 5, sulfur and its compound, specifically the chemistry of sulfuric acid. Something I took you through, my student. Chemistry of sulfuric acid, form 3, 11 marks there. Question 6, a repetition of electrochemistry once again, but this time around is application of electrolysis there. You can see that's form 4 work, 10 good marks. Then you can see question 7, just a question there from salts, form 1. Basically, I think it's salts. Then Hess's law, mole concept. Those are just form 4 and form 3 there. Well, looking at the question, that's how the paper looked like. Well, going on, something here, well, that is good news. Having gone through the paper myself, over 48 marks out of the 80, it is what we have discussed in this channel. So a student who might have followed my channel was able to get above average of the paper. Good, that is question 1. The structure and bonding there, then periodic table continues there. You can see my student. Then periodic table continues, part 2 of B. Yes. What I'm doing is just to present the paper first, the question paper. And then you can see there question 2, a question on alkanos. Yes. A graphical part of alkano there. Moving on. Yes. Answering question from the graph. Going on. Yes, my student, I'm just taking you through the questions. Then you do answer them before we go through the marking scheme. That is question 3, electrochemistry. Okay, a continuation of question 3, that is electrolysis. Moving on, some Faradays somewhere, yes. Question 4, reaction rates. Yep. Now moving on, part B of question 4, reaction rates continue. A graph that was presented, part C of question 4. Yes, using that graph to answer the questions. Okay, the question continues, question 4, then finally question 5. A question on sulfuric acid, chemistry of sulfuric acid. Good. The question 5 continues. That is question 5. Yes. Question 6. Yes. Application of electrolysis somewhere. So those cells. Question 6 continues. Question 7. Yep, question 7, there it is. And question 7 continues, and I'm sure that is the end of the question paper. So my student, what you need to do, because a good revision is where you challenge yourself. Personally, I have all the answers. Yes, so what you need to do, stop the video and attempt the questions. Yes, my student, and here is the marking scheme. As the paper was marked, question after another. Question 1, good, that was the question. You're given the oxides of aluminium and the oxide of phosphorus. So the student was expected to give the structure, the bonding, and the acid-base character of the two oxides. Good, there are the answers. The aluminium oxide is giant ionic. The word giant there was key. You cannot answer this question without the term giant. The type of bonding for aluminium oxide is ionic or electrovariant. The acid-base character is amphoteric. Otherwise, the student could have said it has both character, acidic and basic. Then phosphorus oxide, it has simple molecular. If a student say molecular, well and good. So that is the type of structure for phosphorus 3 oxide. The type of bond, covalent, and it is acidic in nature. Actually, if you dissolve it in water, you get phosphoric acid. That is question 1, part A. Part B, the student was expected to, the student this time round was given a blank periodic table. And if you consider this, my student, it is not the small or the partial part of the periodic table that we're used to. This one, it is actually more extended. And that tells you, don't go just up to 20 elements, then you stop there. Go study the entire periodic table. The student was asked to give the total number of elements in period 1. You can see one box and another one. So it has 2. Okay. Then the student was also to state, the number of elements in period 5. If you consider this is period 1, period 2, period 3, period 4, period 5. My student, if you count all of them, they are 18. Okay, you can see that the two answers for even the marks that was awarded for each. So what does that mean, my student? Remember, there is a block that we call transition element here. It usually have 10 groups. So 10 plus the 8 that we know, 18. So the entire periodic table has 18 per period, especially from period 3 onward. That is question 1B, Roman 1. We go to part B. This part, that is B part 2, Roman 2. This part was easy for students, but a good number maybe did not score. You are given 7 different elements. The student was expected to place them on the table. So how do we go about that? Let's start with element X, whose atomic number is 14. So electron arrangement 2, 8, 4. So my student, it is in period 3, group 4. So period 1, period 2, period 3. Group 4, 1, 2, 3, 4. That's where X is. Go to element Y. Yes, with the highest ionization energy. This one, I think more than 80% of the students did not score. Why is that? Maybe we are used to ionization energy being considered for group 1. But remember, all elements can lose electron. Because what is ionization energy? Energy required to remove the outermost electron of an atom. So what does that mean? The elements that have the highest ionization energy, that cannot easily lose, are the group 8. And the one that has the smallest atom, yes, it's the one with the highest ionization energy. So the element Y is helium. Actually, if you consider the whole periodic table, helium is the least reactive. It cannot gain or lose an electron that easily. Okay, moving on to D is part 3. Z. Yes, the lowest ionization energy. If the highest ionization energy is here, the opposite will be down here. Look at that. The highest ionization energy, the first in group 8. Therefore, the one that has the lowest ionization energy should be the last one here, yes, in group 1. What does that mean? The element here can easily lose electron. That means it has the lowest ionization energy, and that's where element Z will be. Moving on to part 4, element L. It forms an ion with L2 negative. If you see 2 negative means it has 2 extra electrons. It has gained 2 extra electrons. And that means if we can remove the 2, then we will have 2, 6. Remember, the ion has electron arrangement 2, 8. So if I remove the 2 electrons, then I'll have 2, 6. I only need to consider that it is in period 2, group 6. 1, 2, 3, 4, 5, 6. So this is the position. D. D forms an ion with the 2 positive. Yes. And of course, electron arrangement 288. What does that mean? The positive 2 means it has lost 2 electrons already. So if I bring back the 2 electrons, the new electron arrangement for the atom will be 2882. That tells you the atom or the element is in period 4, group 2. 1, 2, 3, 4. The fourth period, here it is. Then second group, 1, 2. That is the position of D, my student. Very easy to locate that. Then element Q, the halogen with the largest atom. That one is easy. The halogens are the group 7. The atomic radius increases down the group. That tells you the bottommost here, it is Q. It is the one with the highest atomic radius. Wow. Very easy marks, my student, to get there. Element R, it is in period 3 and exists as monoatomic gas. The only atoms we know, the elements we know that exist as monoatomic are the group 8. So we only need to follow period 3, yes. We follow period 3 up to the end, and then we indicate R. That is how you're to get 7 good marks, my student, for part B, Roman 2. Easy to locate the position of those elements. If the student decided to mark the elements with their actual symbols, well and good, it was still correct. Otherwise, we move on now to question 2. Well, that is the first part. The student was expected to draw the structure of an alkanol with the carbon, with 5 carbons. So that is N equals to 5. And for that, and of course, give the name. That is it, my student. Very fast. Yes, 1, 2, 3, 4, 5, and OH there. You can decide to show the bonding between O and H, but not necessary because the OH is the functional group. You can see the hydrogens. Remember to fix all the bond. Each carbon should have 5. That is the simplest the student could have drawn, and it is a pentanol. Otherwise called pentan 1O. Pentan 1O. Remember, you can draw the isomers. All the isomers of pentan 1O can also serve as a mark or a answer for that. And maybe that's the question I'll give you, because you can do that for me. You draw all the structural isomers and positional isomers of pentanol. Remember what exactly we're doing, my student. We can decide to remove the OH from here, and we attach it in the second carbon. Then I'll have pentan 2O. That's an isomer. I can decide the OH to be in the third carbon. Yes, then I'll have pentan 3O. I can decide to extract a methyl here. Yes, the outer methyl here. Then I attach it in the second carbon here. Then I'll have a 2-methyl butan 1O. So my student, that is the exercise I'm giving you. Kindly do it for me. Yes, do it for me and for yourself as well. We move on. Yep, we were to do the graph. Yes, good. The student was given this table. Yes, already I've drawn the graph for you, my student. The student was given this table. And the number of carbons, 2, 3, 4. The boiling points there were given also 75, 90.5, 78.5, blah, blah, the way they are given. So the student was expected to draw this graph for 3 good marks. A number of students did not get the 3 marks. I assure you of that. Let's start with the first mark, the scale. Looking at this graph, the student ought to have counted the number of boxes across and the number of boxes vertically, and the plotting, the point you're plotting, be it on the x-axis, the y-axis, must occupy at least half the number of boxes for each case. Now, what was the student expected to do? And remember, you have to use the graph space given, not your own. Let's start with the x-axis, where now we are plotting the number of carbon atoms. We are plotting 2, 3, and 4. So if we try to do any other scale rather than the one I've given, it will not occupy the 3 plots, will not occupy more than half. So what exactly is the student expected to do? You have to assume 1 and 0. And we start from 2. Then we skip 4 squares, 3. 4 squares, 4. 4 squares, 5, etc. At least, if I consider from here, where I'm plotting 2, to where I'm plotting 4, that is more than half the entire space for the x-axis. Along the y-axis, and remember, if you don't want to break, let the 2 start at the origin there. Along the y-axis, I am to plot from 70s to 120. Yes, 70s to 120, it will occupy the space. But remember, the student, you ought to have gone through the question. Because if you're not careful, again, this part I've extrapolated here will not fit. Yeah? And no part of the graph should go outside. So what the student ought to have done is to break the axis and start from 70. And of course, do the marking like I've done for the boiling points there. And then we plot. Having done a good scale, 1 mark. Then we do plot. Where it is 2, it is 78.5. Where there is 3, it is 97.2 there, approximately. Where there is 4, it is approximately 117. So then we do a straight line. Plotting 1 mark, then a straight line. The best line of fit there, up to this point, another 1 mark for 3 marks. So my student, graph work will always be there, but you need to be very keen. Like this one, it was very tricky, especially with the scale. Now, we were supposed to use the graph to determine the boiling point of an alkano with n equals to 5. Going back to the graph, n equals to 5 is not even in the table. So what the student ought to have done is to extrapolate that line. Yes, extend it up to where n equals to 5, then follow that one, and then you read. Okay. For those who did it well, the boiling point there ought to have been 135, 136, or 137. The extrapolation must be shown on the table. That is 136 for my case, plus or minus 1. Okay, we can look at Roman 2. Why the boiling point of alkano with N2 is much higher than that of butane. An alkano has the hydrogen bonding, while the butane, they just have the van der Waals forces, the weak van der Waals forces. This brings the difference, and that is all you need to state, my student, like I've presented that question there. Moving on, alkanos are used as fuel, any other use of alkanos, and then you write the equation for the combustion of ethanol. That is an alkano with N2. There are the points, my students. Yes, ethanol is used as a solvent in the manufacture of drugs. Then it is used as an alcoholic drink or beverages in very low concentration. So over here, my student, if you just say it is used as an alcohol, no. It is used to manufacture alcohols, no. Because itself is an alkano, that is an alcohol. So you cannot just say it is used as an alcohol. Okay, it is used as an antiseptic, yes, as a derivative of very many organic compounds. The combustion of ethanol, you can see the equation. It must be balanced. Moving on, that is Roman 3 there. Yep, you're given the bond energies. Yep, you can see the bond energies for CC, CH, CO, OH, OO double bond, CO double bond. Yes, the bond energies are given. So the student is supposed to calculate the enthalpy change for the combustion of ethanol. And that is the equation. So what exactly is expected of my student? You are supposed to draw the open bonding of this equation. How ethanol is structured, oxygen, carbon monoxide, and water. So that you can be able to do now what we call bond breaking. All these bonds you see on the left hand side have to be broken before they are formed again to just get the products. So like in this case, I have 1, 2, 3, 4, 5. 5 carbon hydrogen bond times 412. Then plus 1 carbon oxygen bond, you can see it there. Then 1 oxygen hydrogen bond, you can see there, 360. Yeah, 360 I think is for carbon oxygen. The one for 348, yes, for carbon. Yeah, of course we have this one. Then we have 463, the carbon OH. Yep. Okay, all I've done here, my student, is to have all these bonds. Carbon, hydrogen, carbon, oxygen, hydrogen, oxygen. All of them added together. If the student is able to do that, half a mark. Getting the answer, that must have the positive there, because bond breaking is endothermic. That is it, my student. 1 mark already. Bond formation. Yep, bond formation. We have now the new bonds that have been formed. Carbon, oxygen. There are 2 molecules, so there will be 4 of them. 4 times carbon, oxygen bonding pair. Then you have hydrogen, oxygen. 2 of them times 3, 6. We multiply there very carefully with our calculator, we get the answer. The negative must be there for the student to score. Now, having done that already, we have the bond breaking energy, bond formation energy. So we need to get the enthalpy change, which is the net energy between the two. So I have this one, I add the 2, and I get negative 1031 kilojoules per mole. Remember, I have just burnt 1 mole. This is a question my student, maybe they don't like it, they fear it, but it is as simple as I've done. But if you do not have this equation, if you are not able to tell the bonding in this equation, it's not very easy to get it. And I think we are done with question 2. We move on to question 3. Question 3, electrochemistry. You're given this cell representation there. Aluminium and lead half cell. The cell, electrochemical cell. You're also given the EMF there. So the student is expected to state the symbol, the meaning of this symbol, the single slash there, this one. Okay. Then write the cell question for this one. So there are the answer. The single slash represent the phase boundary, what we call, or you can say interface boundary, the interface between the solid and the solution. I think in future I need to tell you about what we call the electrode double layer, the representation of that cell, the half cell, how it looks like. Then, of course, you can say it's the interface between the electrode and the electrolyte, and it is still okay. Now, if we want to write the equation, it is aluminium. Yes, you can see it is on the left hand side, reacting with lead 2 ions, okay, to give us aluminium ions, yep, and the lead metal or lead metal. All you need to do is to balance. You may look at it and think it is balanced, but the charges have to balance. Over here we have 2 positive. On this side we have 3 positive. So we balance the charges. Make them 6 by multiplying by 3. Make them 6 by multiplying by 2 on this side. By doing that, aluminium now, you have multiplied the particle by 2. So even the atom should be multiplied by 2. The same case, lead has been multiplied by 3. On this side by 3. That one was the trick there, my student. We move on. Okay. We are supposed to calculate the EMF of aluminium ion is to aluminium solid, that half cell. What are you given? We are given the reduction potential of lead 2 ions is to lead solid there half cell. So, what is the E value for this cell? That's what we're supposed to do. And of course, then part 4, one use of electrochemical cell. Now, let me take you through what I've done. The E cell is always given by E reduction. Yes, remember reduction is a gaining of electron. The particle that is gaining electron, then minus E oxidation. So look at the two. Like let's think about this one. Lead 2 ions becoming lead metal. What has happened? This one has gained electron. So we have said reduction is a gaining. So this is the one we're starting with. We are starting with the negative 0.13, the one that we've given, minus unknown. So the E value for aluminium is not given, equals to this. So having done that, my student, the X, the negative X can be on the left hand side, then the positive 1.53 on the right hand side. Then you add, you get 2 good marks, my student. That is not very difficult to get. Now, you may have forgotten this formula. I want to show you a shortcut of how you can go about it. Look at this one. This one, the lead 2 ions are gaining 2 electrons to become lead metal. So that's a reduction, and the E value has been given. Let's consider this one. Look at this. This one, it is behaving the same. But ordinarily, this one actually is even more reactive, should be the opposite. So what exactly does that mean? I want to do, because I need to reverse this one for aluminium. It appears the opposite. So it will have a positive E value. And that means I can take negative 0.13 plus X, where that X is the reduction potential of aluminium half cell, or the opposite of it, the positive part of it. So I'm saying it is negative 0.13 plus X equals to 1.53. If I do that, I'll get a positive answer, positive 1.66. But that is the opposite of this one. I only need to attach the negative. Otherwise, my student, you need to practice. It is not something that you can grasp that once. And the answer is there for 2 marks. Electrochemical cell. This is a cell. What is the use of cells? So they are source of electrical energy. Yes, like the button cell, torch cell, car battery, computer cell, dry cells, etc. For 1 mark, my student. Don't say they are used as batteries. Yeah, because themselves they are the cells, they are the batteries. So they are used as the source of energy. A question B, application of electrolysis, my good student. Application of electrolysis, you can see, we are doing electrolysis of acidified water. The first part, why is it necessary to add acid, the water? There it is. Remember one thing, water is a non-electrolyte. It is molecular, it has no ions. But to facilitate ionization, for the OH and the H ions to be formed, you add the acid, and then that facilitates ionizing. And that is where now the water becomes a better electrolyte, it becomes a better electrical conductor. Good. State the electrode where oxygen is being produced. Okay, then you write the equation for the formation of that. This is something I've always said. I even discussed it in one of my previous video. When you're given this cell, the longer bar always represents the positive. The shorter bar is the negative. And with that, you can tell. This is the anode, the positively charged electrode, anode. This is the cathode, the negatively charged. So, to answer the question, oxygen is produced at the anode, B. And you're not supposed to write the anode, you write B. Because the 2 electrons have been labeled, my student. It is B. Having said B, then you support it. It is the anode for another half a mark. Or rather, you can say the OH, which are negatively charged, they are discharged at the positive electrode. Anyway, remember the oxygen is produced from the hydroxyl. And that's why we have now the Roman 3. The hydroxyl ions loses 4 electrons, 4 of them, to form 2 molecules of water and oxygen gas there. So that is it. Roman 2 and 3 of part B well answered, my student. Okay. After the electrolysis for 88 seconds, the volume of oxygen produced was 23. So if that is the case, we can now go ahead. What is the volume of hydrogen that was collected? Then the amount of current that was used. So I want to take you through something here. That one, that story I've written there. We are doing electrolysis of acidified water. The half cell at the anode, you can see. This one we have already written. And let's consider here 4 electrons. The half cell at the cathode, my student, ordinarily should be 2 hydrogen ions gaining 2 electrons to form a hydrogen molecule. But because of the 4 electrons, because the number of electrons given out at the cathode anode must be equal to the number of electrons gained at the cathode. So therefore, this must be 4. And that's why I have balanced this equation with a 4 here. 4, 4, 2. Yes, so that this number of electrons must be equal to this. The number of electrons at the anode and cathode must be equal. So that tells you if I'm to do the overall equation is as I've given. And this is where the story is. For every 1 volume of oxygen, 2 volumes of hydrogen will be produced. So do we know? Yes. Do we know the volume of oxygen that was produced from the previous question? Yes, 23. So what do you think will be the volume of hydrogen? 23 times 2. There it is. And actually, this is how this diagram will look like. Anytime I have oxygen here, electrolysis of acidified water, this one, the volume here will always be half the volume here, or they are vice versa. So the volume of oxygen given or produced will be 46. 23 times 2, 46. As simple as that for 1 good marks, my student. You can see that. Tick 1 mark. Amount of current that was produced. Yes, my students, stop and think. We are now into Faraday's Law. Faraday's Law. Faraday's Law requires you to having written a very nice, balanced half-cell equation for the gases that are being produced, like for this case. Now, let's go back to the Roman 4. We are talking about volume of oxygen that was used is 23. So, how do we go about that? For oxygen to be produced, 23, the half-cell equation is as we have seen here. There must be 4 moles of electrons. That translates to 4 Faraday. Yes, if that is 4 Faradays, it means 4 times the Faraday's constant. So this is the quantity of electricity that is used to produce 1 mole of oxygen. If this one produces 1 mole of oxygen that occupies 24,000 cubic centimeters, so how many coulombs will give or will be equivalent to 23? I hope my student, you're getting that. This is molar gas volume. Actually, for getting the molar gas volume, a half a mark. For multiplying by 4, a half a mark. Now, for doing the cross multiplication, another half a mark. Remember, a student can decide to work out the number of moles. 23 divided by 24,000. The number of mole of oxygen used. Then later multiply by the 4 Faraday there. Multiplying by this, a half a mark. Getting the quantity of electricity equivalent to 23 cubic centimeters, a half a mark. Okay? Then we move on. Quantity of electricity is always given by current times time. Okay? That tells you that current will be given by quantity of electricity, then divided by time. The quantity of electricity, this figure here, divided by 88, you get approximately 4.2 amperes. That is one way of doing it. Not very difficult, my student, there, but follow and revise. Now, alternatively, you can decide to use hydrogen, the 46. Okay? And how do you go about that? There it is. You argue like you have argued there, but now we are working with 2 Faradays. Yeah? Let me take you back to the equation. Over here, for 1 mole of hydrogen to be produced, here I'm talking about 2 here, but for 1 mole of hydrogen to be produced, I must be working with 2 electrons, 2 moles of electrons. That means 2 Faradays. Yeah? If it is 2 Faradays, my student, it means when I'm working out there, I should use 2. And I work out like I've worked before, the answer will be the same. This one, we are working at room temperature and pressure. But the question did not specify. A student can decide to work with standard temperature and pressure, STP. That tells you the volume here will be 20 to 400 cubic centimeters. And the working will be the same, but the answer will be a bit different. Let's move on, my student. Question number 4. Yes, rates of reaction. Yes, explain how a catalyst will affect the rate of reaction. A catalyst will always speed up the rate of a reaction. 1 mark. The reason for that, it will lower the activation energy. Another mark. How does a catalyst affect the yield? A catalyst and maybe to support that, look at this graph, my student. This is a graph showing 2 reactions for the decomposition of hydrogen peroxide. The first one is a catalyzed reaction. The other one is uncatalyzed. So what exactly happens? When you use a catalyst, the first reaction takes a shorter time. Yes, maybe a shorter time to go to a completion. The other one will take a longer time. But the 2 graphs will have to go constant at the same volume. And that tells you the yield for the 2 reactions are the same. So the catalyst will not affect the yield, the total yield for any reaction. So what exactly will it do? A catalyst will just speed up the time taken for the yield to be produced or the reaction to go to a completion. Moving on. Yes, my student. That question. Yes, you're told that the rates of reaction are measured using different methods. In the decomposition of hydrogen peroxide, the rate is measured by recording the volume of oxygen gas. So other than measuring the volume of the gas, describe how you can measure the rates of reaction for the following. A thiosulfate reacting with an acid to give you sulfur and whatever, that is sulfur oxide and water. So how can you tell that? That's a reaction that is in book 4, my student. We have done it severally. We've done it severally. So what exactly do you do? There it is. You need a piece of paper. You mark it. Whichever the mark you do, you do an X, yes, a cross. Then you place a beaker. You add hydrochloric acid or the thiosulfate, whichever one you start first. Then add, of course, the other reagent, time. Yes, how long it will take for the paper to be completely invisible or to be completely obscured. That is an experiment I know in very many schools we have done. It's a matter of describing that. You can read what I've just written there. Alternatively, you can do the reaction on a weighing balance. You place a beaker on a weighing balance, yes, turned on, that is. You add sodium thiosulfate, then add the HCl and immediately start recording the change in mass until where the mass becomes constant. That is B Roman 2. We move on. That is B Roman 1, B Roman 2. Acidified potassium manganese 7 and iron 2 sulfate. How can you tell the rate of reaction? The same story. You place the 2 solutions in a beaker and immediately record the time. Yes, start a stopwatch. Record the time it will take for the purple color to go colorless. That is that. Part C, you are given that graph. Remember, you're talking about the same thing, the decomposition of hydrogen peroxide. Volume of oxygen against time. You can see the graph there. So we write the equation for that. As simple as it is, hydrogen peroxide, my student, acted upon or in presence of manganese 4 oxide, you get 2 moles of water and oxygen. That one, my student, you only need to know how to write equations. And it is well written, well balanced. The rules of writing a chemical equation: it must be well balanced. The state symbols must be there. In case they are missing, a half mark will go. Then, my student, the formula of the compounds must be correctly written. We move on. Yes, we use the graph to determine the number of moles of oxygen that was produced. Then the concentration of hydrogen peroxide. Now, from the graph, we must get the maximum possible volume. And this graph, there was a half a mark here for reading the volume. but majority of the students still did not get it. Why? Some of them do not have the skills of reading the scale. Like, look at this one. From 0 to 1 centimeter, it is 10. Okay, represent 10. How many small squares? 1, 2, 3, 4, 5. 10 divided by 5, 2. That tells you one very small square represents 2 cubic centimeters. And this graph became constant or horizontal here at one box after 110. So this is 112. The majority of the students were stating 111, some 114. I don't know where, but that is half a mark. Having gotten half a mark, the molar gas volume was given. It is equivalent to 1 mole. So what about 112 cubic centimeters? So by doing that, 112 divided by 24,000, you get the number of moles. The marks distribution as I've given. The next question was to determine the concentration of hydrogen peroxide. The equation will help you because already we have the equation here. That tells you for every 1 mole of oxygen, I need 2 moles of hydrogen peroxide. And that tells you the number of moles of hydrogen peroxide will be twice the number of moles of oxygen. You multiply there by 2, my student, you get that half, yes. Then remember you're given this, you're given over here, we are working with 50 cubic centimeters of hydrogen peroxide. So how are you going to argue? If 50 cubic centimeter has this number of moles, what about 1,000? Or rather, if you're good in mastering the formula, maybe it will be there to help you. 1,000 times moles divided by volume. So you multiply that, you get 0.18668 molar. A good question, my student. These are questions for those who have practiced moles, easy to have. Okay, moving on. We are supposed to determine, yes, as you can see that part 4, the rate of decomposition of hydrogen peroxide at 18 seconds. So what we need to do, my student, is to go to the graph. At 18, we follow up that vertically. At that exact point, do a tangent. And this is a question that was there in KCSE 2021. And the majority of the students did not get. So those who revised it well, I think they got it. A tangent at 18th, a tangent. Then, of course, get the gradient of that tangent. So like the one I've done there, it's a good guide for you, student. Then you can read like the 2 points. Over here, I have a point, 29.5 and 120. Yes. And then 11 and 80. Then do the gradient. Change in y over change in x, half a mark. Getting the answer there, the unit must be there, cubic centimeters per second, another 1 mark. Moving on, the student was expected to state the factors that can increase rate of decomposition of hydrogen peroxide. Well, what exactly can you do? The student can do the heating or increase the temperature that will increase the kinetic energy of the particles. The student can also increase the concentration of hydrogen peroxide. That will increase the number of decomposing molecules again. Or rather, it can also increase the number of collision. That is collision theory. That is the end of question 4. We move on to question number 5. How can you prepare sulfuric 6 acid? Starting with sulfur 6 oxide. As I've given it there, you dissolve sulfur 6 oxide in concentrated sulfuric 6 acid. That is the first step. You get oleum. Oleum is diluted now or reacted with water. Then the reason for doing that, the trick here is, why can't we go direct? Dissolving sulfur 6 oxide in water. The reaction is highly exothermic. Another whole mark there, my student. Maybe the question was not very clear of the direction the student should take, but just answering the way I've written, the student was to score 2 marks. Otherwise, the student could have argued that the sulfur 6 oxide is dissolved in very cold distilled water for a whole mark. Then the reaction, if you do or react in ordinary water, the reaction is a highly exothermic. That is it. Part A. Part B, concentrated sulfuric acid acts as a drying and a dehydrating agent. You give an example of a gas that can be dried using sulfuric 6 acid. Then you complete these two reactions. That is it. All gases except ammonia, hydrogen sulfide, sulfur 6 oxide, because you've seen it can react with conch, sulfuric acid, and a good number of alkenes, because they can easily be reacted or they can be converted to alkanos. But the rest of the gases, hydrogen, oxygen, carbon 4 oxide, nitrogen, chlorine, carbon 2 oxide, sulfur 4 oxide, etc., HCl, etc., they can be dried using sulfuric 6 acid concentrated. The reaction as you given there, sugar can be acted upon by conch sulfuric acid. You get carbon and water. Hydrated cobalt 2 chloride can be converted to anhydrous cobalt 2 chloride and water. The equation as I have given. Moving on. Now, remember, this is an observation for the previous part. When you have sugar, what exactly do you observe? Sugar will be converted to carbon. That is a black solid there. And of course, water will be formed. If it is hydrated cobalt 2 chloride, that is pink, it will be converted to anhydrous cobalt 2 chloride, that is blue. And of course, water will be formed. So to answer that question, there it is. If it is sugar, whether it is brown sugar, white sugar, it changes to black. Droplets of a colorless liquid, heat will also be generated. With the second part here, the pink crystals or crystals will form blue powder. That is it. Crystals changes to powder. That is still an observation. And then droplets of a colorless liquid there. Good. How is sulfuric, in which way, or rather, what are the properties of sulfuric acid in this case? In this one, you see sulfur, then sulfur 4 oxide. So this is an oxidizing agent. It is being oxidized there. So in this case, oxidizing agent. In this other case, you can see it is all about volatility. As we say, sulfuric acid is less volatile. Hence, it can displace the more volatile acids like nitric acid from their salts. So that one I've discussed in the notes, not even once. So my student, you need to know that. We move on. Part D. Yep, we can do esterification. Whatever is given there is esterification process. So what is the use of concentrated sulfuric 6 acid? Because we add drops of sulfuric acid. Then the formula of the compound formed above. Remember what we're doing. We are reacting. This is ethanoic acid and mixture and ethanol. Ethanoic acid and ethanol. What exactly do we form there? So the answers for this one, yep, my student. In the first case, sulfuric acid is a catalyst. And it can also act as a dehydrating agent because esterification process leads to formation of an ester and water. So the conch sulfuric acid can also absorb the moisture of the water there about. The formula of the compound formed, we are talking about ethanoic acid and ethanol. So we start with ethanol. It gives us ethyl, and this one gives ethanoate. So the compound there is ethyl. You can see the tail, ethanoate with the 2 carbons there. Either the formula will serve as an answer, my student. Moving on now to question number 6. Question number 6. Yes, a question that is even the teachers, the examiner did not expect it. Because we usually teach electrochemistry, but when it gets to that, maybe we do ignore or skip. Because it is towards the end of Form 4, we are done with the syllabus. So dealing with this question, maybe many teachers have always assumed or just covered it in a hurry. Now, there are several types of cells that can be used to electrolyze brine, concentrated sodium chloride. One of them is called the Mercury cell. So the first part, we were to name other types of cells. Then why Mercury cell uses titanium and graphite and not steel, okay, as the anode. Then part C, why at the anode chloride is being discharged, not hydroxide. Then moving on, part D, we write down a question describing how sodium hydroxide and hydrogen are produced. Okay, this one, I think for most students it got them offside. 2 reasons why mercury is recycled. Then the uses of chlorine and sodium hydroxide in paper industry. Okay, what I've decided to do with this question is to extract the content from the book, direct from KLB book 4. And then we discuss and we see that all the answers were there. For the student who had covered this in the book 4, all the answers were there and the student was more advantaged. Good. That is it, as it is in the book. You can see that is manufacture of sodium hydroxide, chlorine from electrolysis of concentrated sodium chloride, brine. The stories are given there. This can be done using the Mercury cell. And part A, we were to name other types of cells. And which are these other types of cells? I'm going to discuss down here. But before that, we can answer part B. The electrolyte in the Mercury cell is concentrated sodium chloride. Yes, brine. The anode cell is made of carbon, that's graphite, and titanium, because they do not react with chlorine. So the answer for the question, it is almost there. Why can't we use steel? Steel is made of iron. So the iron in steel can react with chlorine. Or rather, you can say steel reacts with chlorine. Good. That is the answer for part B, for 1 mark. But let's look at the mercury cell. There it is. This is a diagram of a mercury cell. You can see the electrolyte here, the brine, it's fed in. What you see here, the positive, these are the graphites or the titanium. They are the anode. Of course, the mercury will be the cathode. The flowing mercury will be the cathode. And the products for this, there are always 3. Sodium hydroxide and hydrogen. Both of them forming at the cathode. Then at the anode, you can see chlorine is coming out. This one is being formed over there. Now, in the other cells, there it is. This one works more or less the same as the mercury cell. It is called the membrane cell. The membrane cell. Again, concentrated sodium chloride is the electrolyte. The products coming out from the cathode, we have sodium hydroxide, we have hydrogen. At the anode, chlorine is coming out. So this one is called the membrane cell. For the high schoolers, maybe this is the first time you're getting to see this. Moving on, good. This is another one. On the diaphragm cell. It works more or less the same as the mercury cell, as the membrane cell. The electrolyte, as usual, brine. Then you can see the product. This one is at the anode, you can see chlorine. At the cathode, you have hydrogen, you have sodium hydroxide. So the question was, how do you form hydrogen and sodium hydroxide? Both of them will be occurring at the cathode, not at the anode. Of course, you can see some of the reactions that are taking place there. But we can move on and discuss this part. Part C. Why is chloride preferentially discharged? Okay, it is just because the electrolyte is highly concentrated. So the concentration of the OH is low compared to that of chlorine. So the chloride, that is. So the chloride ions will preferentially be discharged because they are highly concentrated in the electrolyte. That is it. Moving on, part D. We were to discuss this, or the student was supposed to discuss how sodium hydroxide and hydrogen will be formed at the cathode. Using the equation, remember the student was instructed, use the equation. Here it is, the first equation. Sodium ions gains electrons and form sodium metal, or sodium metal, the first equation. Writing in words and you have a mark. But if you write in full in equation, 1 mark. Then going on, the sodium so formed here reacts with the mercury to form what we call sodium amalgam. Sodium amalgam, you can see that. A mixture, it's more of a mixture than a compound. Okay, then the sodium amalgam will react with the distilled water. And when that happens, sodium hydroxide, mercury is regenerated and hydrogen gas is formed. I think for many students all over the country, maybe 10% or less were able to do the 3 questions. Now, part E of the question, why is it important to recycle mercury? 2 reasons for 1 mark each. Mercury is very expensive, okay? Then mercury is very poisonous. We need to ensure that it's not getting into the environment, my student. We move on. That is part F, uses of chlorine and sodium hydroxide in paper industry. Chlorine is used as a bleaching agent. Sodium hydroxide can be used to soften or to digest, to decompose the wood pulp there. Wow, that was question number 7. A very question that nobody expected. So that tells you, my student, the trend is changing. The setting trend is changing. There are some parts of the syllabus that we ignore. We assume they can easily be tested, highly tested. We move on to the very last question, my student. Good. 2 ionic compounds, formulae. Underline that, formulae of 2 ionic compounds that can be used to make lead 2 sulfide. Sulfide. Maybe majority were confused by sulfate or sulfite. So then you have an equation to write here. 2 moles of aqueous ammonia reacting with 1 mole of phosphoric acid, you give the product. There it is. Lead 2 nitrate, half a mark. Sodium sulfide, a half a mark. Remember, any soluble salt of lead can work, but in high school I don't think we can have any other. It is lead 2 nitrate. Remember, any metal in group 1, sulfide will still work for the second half there. Or rather, you can say hydrogen sulfide in aqueous state. And that is how you got that. Remember, this is formula, my student, not words. Then we had a very tricky question that I think very few people got. 2 moles of ammonia reacting with 1 mole of phosphoric acid, you get ammonium, diammonium hydrogen phosphate. The way I've written that equation, my student, nothing else. Let's go on. You had a question here on application of Hess's law. Anhydrous copper 2 sulfate, you add water, you get hydrated copper 2 sulfate. Then hydrated copper 2 sulfate is converted to aqueous copper 2 sulfate. You can start with anhydrous copper 2 sulfate, you go direct. Okay, so this is hydration. Yes, this is this hydration from hydration. Then again you heat dehydration there. This you can dissolve direct. Now calculate the enthalpy change for this process. Anhydrous copper 2 sulfate, where is that? Here. Yes, you add water, you get hydrated copper 2 sulfate. The enthalpy change here. Okay, over here. So how do I go about that? Vector method, my student. You go this way, then you go this way. That tells you it will be, as I've done, negative 156 kilojoules, yes, minus, now this will be minus 12 kilojoules. You get this, half, mind the unit. If you do not have the, you don't know the unit, or you have forgotten that the units are here, do not write them. If you write the unit here, should be the right one. Mind this K here. It should be lowercase k. If you write the capital K, that means Kelvin. So, and the unit, the examiner will just, interpret it to be the wrong units. So, mind the units there, my student, for that second half mark. Describe how you can prepare hydrated copper 2 sulfate from aqueous copper 2 sulfate. Then anhydrous copper 2 sulfate from the same. So, how do we go about that? There it is. In short, we are trying to do crystallization in part 1, and in the second one we're doing evaporation. You heat the aqueous copper 2 sulfate to saturation, 1 mark already, it's at home. Then you allow it to cool and crystals will form. My student, it is as simple as that for 2 marks. The second one, you heat copper 2 sulfate solution to dryness, and that is it, half, even dryness half. In case you want to continue from part 1, because already part 1 you had made or prepared hydrated copper 2 sulfate using aqueous copper 2 sulfate, then what you need to do, you heat the crystals obtained in part 1 above to dryness or until the blue crystals changes to white. As simple as that, my student. Wow, we are heading to the end of the paper. Aluminium hydroxide is an antacid. Any other antacid? Then you have a mole question here. Concentrated hydrochloric acid in the stomach, 0.01 molar, is an antacid. Is of course the gastric juice there. Then we use an antacid with aluminium hydroxide. Then the question is, we determine the mass of aluminium hydroxide that will be contained in the antacid. Good. Another antacid we know, milk of magnesia, or magnesium hydroxide, or magnesium oxide can also do. Now, let's do this question here, Roman 2. The equation is very important. Why do we need the equation? We need to know the reacting mole. Aluminium hydroxide is to HCl. We need to know what exactly is the mole ratio there. Then, having known the mole ratio, half a mole, we go ahead to work out the relative formula mass of aluminium hydroxide. Everything has been given, 78, half a mole. Moles of HCl, using the formula or interpreting this, using the first principle, 1,000 has 0.01 mole. What about 100? By working out that, you get the number of moles. Remember, it's not a must. I see the answer here, but I must see the working around here. A half a mole. Then moles of aluminium hydroxide, it is guided, or we are guided by the mole ratio. It will be a third of the moles of HCl. So I divide by 3, another half mole. Then mass, I think this should be mass, my student. Mass of aluminium hydroxide. It is the number of moles multiplied by 78. And you get the answer there in grams. Good. I think I deserve some claps. We've done some good work. We've gone through the paper. Thank you so much, my student, for watching. Maybe what I can do, special gratitude. Thank you so much to my seniors. Because I'm Dr. Sirme, but I'm not Mr. Know-It-All. I have my good seniors in 2-3-2. My mom there, Madam Virginia, thank you. Ndichu, thank you so much for watching this. I know you do expose your student to my content. A good friend of mine, Reverend Boniface Makanga, thank you so much, sir. God bless you, God bless you. All the 2-3-2 examiners, thank you so much. And all the fans of Dr. Sirme YouTube channel, thank you so much. Good, that is the end. Looking forward to revise the paper 1 and both mathematics papers on this channel. God bless you. Happy New Year 20.